Good morning. Welcome to Krishna's class. We briefly recall some of the facts that we introduced last time. And this is essential because we want to get the continuity for our lecture. So where we started last time was to drop the condition that A is finite. So we shall assume that drop the condition that the index set then of course there is a problem that comes up, namely that what do we then by the sum where of course because phi is now taken as a map from A to with this condition. And what do we mean by this sum? We have to attribute a meaning to this. If A is finite, then it is obvious what it means. That is what we have looked at already. If A is countable, then you take partial sums of this finite partial sums and construct a sequence and then go to the limit. So through the limiting process we can attribute a meaning. But what if the index set is uncountable? So we have to explore this first. Okay. First of all, we will give a meaning to this. So we gave the following meaning. We said that then denotes the supremum of the set of all sums phi alpha 1 where of course alpha 1, 2, 3 etc. n is a subcollection of this, or alpha 1, alpha 2, alpha n is a subcollection of the set A. Okay, right? It's a finite sum. So you take every finite subset of A, find out the corresponding sum, and then take the supremum of this. After all, you know that this is greater than or equal to 0. This may be bounded or may not be bounded depending on whether pi alpha takes the value infinity or not. Okay. If any one of these sum is infinite, then certainly the sum is infinite. But otherwise, it may be the situation that all these partial sums that you take, the finite partial sums that you take, are finite, okay, and bounded so that the supremum exists. And if that is so, that supremum is what you call the sum sigma alpha belonging to A pi alpha. So that's the meaning to it. So we have fixed the meaning now. And now you can see that this sum is a Lebesgue integral of phi relative to the discrete measure or what you call the counting measure U1. What is that? See, you have got A, the power set of A, and B. Now you take the cardinality of each element of PA. That cardinality is the number that is given as mu. So mu A, mu of equal to the cardinality of S, where S is contained in, is an element of. So if it is finite and consisting of say n elements, then mu of S is equal to n. If it is infinite collection, then it is going to be. Okay, so that's how the measure is set, and you know that it's a Lebesgue measure. Okay, then this becomes integral over A of pi d. Okay, right. Now let us this is just a change of notation for this purpose alone. Okay. Now a complex function phi with domain A is in L2A. We are interested in L2. That is P equal to 2. That's the case P equal to 2. If and only if is finite. This is essentially the same as integral over A mod is finite. So this is the same as this. So we consider such functions. Likewise, you have for any LP. For LP, you replace that 2 by P. So now you see that the collection of all phi in L2A now one can see that this is essentially for phi. Finite and is L2 is L2. This is L2A. Now we have an inner product on this space and this is these are the, so this is the induced now. Okay, and the inner product is given by this. Right? So we have these numbers, and you can show that if L2A, then the product phi psi belongs to L1. This is one of the simple things that you can get. And therefore, this is well defined, and this is essential. Phi psi bar B. Right. So there is something special about this sum. At the outset, this sum may be an uncountable sum. Okay? And we have already attributed a meaning to it. And we prove a little theorem, or we have proved a little theorem, which says the following, that, so theorem, L2A, remember A may be uncountable. At most. That means only at most at a countable set of points, phi may take non-zero values. Almost all points other than a possible countable set of points, the function phi will be 0. This is the property that you can prove. And this we have proved, and this is very interesting because you see that although this sum appears to be rather, sort of threatening type of uncountable sum, but you see that essentially this reduces to a countable sum. So essentially, it may be a finite sum or it may be countable sum, but it cannot be an uncountable sum. This is the inference that we make, and the proof we have already explored last time. Okay, so these are the preliminaries that we have explored so far. Now what we look at the following. Now we come back to our main theme. So let H be a then U alpha a orthonormal image. This is an orthonormal collection image. I don't assume it's a complete orthonormal set or anything. Those things we will discuss later. But right now, it is just an orthonormal collection. Okay. Now, we want to explore the following. So, you see that, suppose okay, let us look at some example. Consider for a three-dimensional vector space. Let now you see, you look at the span of this. U1, U2. So this is a two-dimensional. Orthonormal subsets are all linearly independent. Therefore, this is a subset of R3. Geometrically, M is a plane passing through the origin to the origin plane passing through the origin containing the vectors U1 and U2. So, pictorially it is going to be something like this. Suppose this is a picture of R3 and you take a plane and suppose this is U1, this is U2, orthogonal, and U1, U2 constitute what is called a basis for this particular plane. So this is a subspace of, this is a two-dimensional subspace of R. Okay. So M is a it's a two-dimensional subspace of R. Now what we have is, we consider L2A. What is L2A? L2A consists of all x hat x hat 2 such that or in other words you take an element x belonging to what is that? 3. Then x is equal to x hat 1 equal. Okay, so it's a linear combination of that. Then we have, this implies you have the x hat 1 x hat 2, this ordered pair belongs to the span of belongs to R4. Okay, where you see you define this x hat 1 is equal to the inner product of x with 1 2. This is what you okay. So you project any vector x belonging to M, it can be resolved uniquely as this one. Okay, now see what you observe is the following. Okay. Let me call this P. Okay. Now in this case, what happens is that since it is finite dimensional, is closed. Is closed and one. This P is a subspace, therefore it's a convex space. P is a closed subspace because it is finite dimensional. If P is not finite dimensional, then your P closure may not be equal to, okay. So But in any case, it is convex. Okay, so these properties are there. Now, what you can prove is this, that every element in every element in L2A can be two. An element in the two-dimensional space L2A. So A consists of 1 and 2. So corresponding to that, you have U1 and U2. So it's a span of, which is essentially the span of right. So the map X to X hat alpha this belong to L2A. That is, what is that? That is X is identified with the ordered pair this is the identity. So you denote this by map F. Then F is linear, F is continuous. F is both linear and continuous. And F is onto F is onto L2A, where A is of course taken as onto. Now, suppose P is the span of what have we said? Called suppose suppose this is the span of U1 U. This is two-dimensional. Then F is F restricted to what? F restricted P is a isomorphism of an isomorphism of R ordered pair x1 x hat 1 and x hat 2 which is also an isomer. Okay, so this is the scenario that you have in 3 dimension. In 3 dimension, suppose you take two linearly independent vectors. There is a plane passing through the origin spanned by these two. When these are orthogonal vectors, U1 and U2. Okay, then you take for an x belonging to H, x hat belong to R2. So you have an essentially two, and this is a replica of what is called L2A. Okay, so this x is x. You see, you have a map f of x belonging to R2. F is linear. F is linear, continuous, and on. Now you see that if x belongs to span of U2, then F is 1 to 1 and onto, and also linear, therefore it's an isomorphism and is an isometric. So this is the result that we observe. Okay, it's very simple. See, so what I geometrically it is very easy to explain. Geometrically it is this. You have a three-dimensional space. Okay, this is a dimension. Okay. Now, to take so you have a subspace. So U1, U2 orthonormal vectors. So they are linearly independent. So you look at the span of this as M. Then what you get is you can find in R3 or a two-dimensional space R. Okay, so that if you take a element, if X belongs to H, then X can be mapped to R. Okay, X belonging to H, X can be mapped. Now this map, so you are writing a function now this is in R2, this is in, so X belongs to, this is the scenario. Okay, now this, what we can say about this map is that F is on to R. F is on to R. F is continuous. Continuous. Okay. Now what one does is, so you restrict F to M, where M is the span of then what happens? Defined by f of x equal to where x is equal to then of course f is linear one-to-one and onto. This is one-to-one because an isometric. That means between two vectors in M, the distance is the same as the corresponding vectors in R2. So you take an element here, X, then you have so this is the map F that. Okay. Now this is a linear map. This is an onto map. You see that the whole Fm will get mapped onto this two-dimensional space. It's an onto map. And also it is one-to-one because if you take x and y belonging to this, then the distance between x and y is the same as the distance between x hat 1, x hat 2 to y hat 1 to y hat. Okay, so that is the picture. We'll try to prove this theorem in general. Okay, with no assumption that, dropping the assumption that the set A is finite. It's now not even assumed to be countable. Okay, so that's our objective. The objective is, you identify, see, take H, U alpha is a set. Then you take X belonging to H. Now X you can put to correspondence with the alpha belonging to A. This is an element of L2. This is an element of L2. So you are taking a map from H to L2A. Then F is onto L2A. F may not be one-to-one. Okay. Secondly, what you have is, suppose F is restricted to M, where M is equal to span of 2 alpha. Okay. That means you are choosing X from here. Then F restricted to them is a linear map on M with range L2, range L2, one-to-one, onto, and continuous. Further, it is an isometric. That means it's a distance preserving map. In H, you have a distance defined through the inner product. In L2A also, there is the distance that you define through the L2, small L2 norm. You see that if the distance between, this one it is, norm of X is the same as equal to norm of this is the L2 norm. Okay, that is the distance between X and Y is the same as the distance between their images. In the span of or in L2A. So this is both. This is M. I should put here M. M is that's the result that you want. Okay. So our objective is this. Now to prove this theorem, there are various little things that you have to prove here. So we do the following. We establish a lemma. This is a very general result. This is a very general result. Just nothing to do with the vector spaces or anything, just to do with metric spaces. Okay. Suppose metric spaces. We are not even assuming that they are linear spaces. Okay, not necessarily linear spaces. X is assumed complete. That is the first assumption. The second assumption is f is continuous. C D so you have two spaces, two metric spaces. Then we make the following conclusion. Very general theorem. So remark, I want to make a remark. We are not assuming X and Y are linear spaces. This is a general. We are not assuming X and Y are linear spaces. We are merely assuming they are metric spaces. Okay, we are assuming X complete in the sense that all the Cauchy sequences do converge in that space. Okay, that is the first thing. Then we have, so we take f from x to y, f continuous. You can easily see that there is a machinery to talk about continuity because x is a metric space, y is a metric space. Therefore, you are talking about a map from x to y, which is assumed to be continuous. These are the assumptions that you have. Then x has some dense subset. X naught on which f is an isometry that is x naught closure is equal to x is one thing. The second thing is that d, let me put here x of equal to this is what you mean by isometry. That means the distance from x to y is the same as the distance from fx to fy. So it is a distance preserving map. F is a distance preserving map. That is the meaning of isometry. Okay. Then what we can prove is F is an isometry of we'll prove this. Yeah. Let us first prove this result. The first thing that we want to prove is this. F is an isometry Okay. So let us. So what are the essential information that we have? We have X complete. This is one thing. Then F continuous. Okay. Then X on X naught. Sure. On X naught. F is an isometric. Okay. These are the assumptions that we have. Finally, then what we get, the f of x naught y. With these assumptions, we can conclude y. These are the assumptions that we have. Okay, so we first prove f is an isometric. So what do we have to prove? Since f is continuous, and Cauchy sequences x naught such that or zero as n tends to, that's the thing. And similarly yn dy sorry yn that is, these are Cauchy sequences. These are Cauchy sequences which converge to. Now we know that, let us compute this. D of, that means we are looking at the distance of fx to fy in the y space, because we are already there. Okay. So you can call this dx dy. These are the two spaces. So F is a map from this space. Okay. So dy fx fy are elements in y. Okay. So the distance between them is essentially equal to limit n tending to infinity of d of dy of fyn, which is equal to limit n tending to infinity of dx of because this is a continuous map. X, the distance function is a continuous map. Okay, therefore this is a here we have used the continuity when you write this. Okay. That is something that we do. Now we want to prove that f is also on. This is the next condition. How do we prove that? Choose some y belonging to y. There exists a sequence. There exists a sequence in X such that f of xn converges to y. Cauchy sequence. In y. Now since f is an isometry, x naught since X is complete, this is where we use this. There exists an X belonging to X. Such that the sequence Xn converges to X. By continuity of F, we have n tending to infinity of f of Xn, which is essentially equal to, therefore Xn converges to X, so that completes the proof of this. Okay, so this is a general theorem in the sense that we don't bring in our ideas of linear space structure or into the situation. This is valid in a more general setting where even if you assume they are just metric spaces, the result is valid. Okay. Now, what I intend to do is I apply this to prove the result that I was discussing earlier. Okay, so we come back to our situation. So I shall do it in next lecture. Thank you very much.